fonts are available for other students. So I was saying that you should be able to do this one. If you won't be able to do this one, I want you to speak up saying, Miss, we cannot do this. Please record yourself doing it for us and give us extra assignments, anything you want. So how do you feel towards this one? Do you know how to plot U versus I? Do you know how to find the slope using Excel and using your calculator? Do you know how to deduce R from the slope? How do you feel, confident or not? You can simply say, we don't know any of this. It's okay. Please speak for yourself. Yes, Nazir?
I calculated the slope on the line in Excel. I did it correct, maybe I'm not sure. Can you send me the mistake or the solution? I just want to check if it's correct or wrong.
Okay. Did you send me your work?
Yes, I sent the part.
Did I reply with a correction?
Yes, but you didn't get it wrong. You didn't put it X or you didn't correct it.
Okay, so I sent you a file that is not corrected?
I don't think so. Like, I think it's correct. Answer the work.
Okay, because I remember, okay, Nazir, since we're speaking up and you can see my screen, if I'm not mistaken, I sent you this. Is that you? Because I don't have your name on it. Let me try to check it out. It doesn't say, is that you? Nazir?
No, it's not me. It's not me. No.
Okay, so probably I send this for someone else. Anyway, let's communicate privately via email. If you need help, anyone, please let me know, okay? So you are supposed to know how to solve this alone. That's concerning data analysis number 2. Concerning data analysis number 1, you need to know how to find the averages and okay, so let me open it for you because I really believe it's very important. So data analysis number 1, everyone in this room should be able to know how to count number of sig figs, how to find the average and the error on it, this one, average and the error on it, and how to do the propagation of error. This one is solved for you, and this one
Doctor,
is new. Yes, Rima.
I have a problem regarding the Ohm's law. I couldn't solve it.
The one that states find the error on R, or was it this?
Yeah.
Or was it data analysis number 2, where you need to plot?
No, the error on R.
Okay, this one, what you can see on my screen. How about we do this together right now, so everybody else can hear it? You agree? Yeah. Okay. Anybody did this one?
Yes, I did it.
Okay, I want you please to assist me.
I did it.
Okay, Nazir and Joseph, both of you did it, right? Okay, I want you please to assist my work.
Me too.
Okay, yes, you too. So, can you please tell me how you found R? What was the method to find R?
First,
so U over I, right? Okay, so which means it's 3.2 divided by I, which is 20.02 milliamperes. We need to convert to amperes, so 2002. Am I right? So I just divided by 1000 to convert to amperes. So I'm gonna say divide by 1000 to convert to amperes. Okay, keep that in mind. Okay, so what is the answer for this one? You should always have your calculators close to you. My calculator just gave me this one. I'm not gonna round it. I can write ohms if I want, or volts per ampere. I will keep it as such and wait until I find the error on R. How do I find the error on R?
Propagation of error.
Propagation of error. I'm gonna get a new document for us, so I will be able to use it as a whiteboard and maybe draw on it. Give me a moment. Okay, perfect. Am I glitching? today? Or is it good?
Oh, that's good. That's good.
Okay, so draw. Okay, I have U to be equal to R over I. That's, no, actually I have R to be equal to U over R. So R is equal to U divided by I. That's the function. To be able to find the error on R, how many variables do I have? I have this and this, right? So I have two variables or two measurements, or am I wrong? Yes? So here in this case, I should open a big radical, exactly like the Pythagorean theorem, under which I should open a big parenthesis squared plus another big parenthesis that is squared. I have only two parentheses because I have two measurements, okay? And under this one, I should write the derivative of R, which is my function, over with respect to U, okay? And then I'm gonna do the same exact thing, but it's gonna be the derivative of R with respect to I, okay? Are you with me? Then I should multiply this by the error on U, yes, and multiply by the error on I. So the error on U is here, 0.1 volts, and the error on I is this one, 0.04 milliamperes to be converted to amperes. So this one has to be, again, let me move this to the side to be able to see it. Okay, so this one is gonna be 0.1 volts, and this one is going to be 0.04 divided by 1,000, which is 0.04 divided by 1,000. If you want, you can write simply 4 times 10 to the negative 5, because I hate writing all these zeros, times 10 to the negative 5. This is easy to write. But then how do I do the derivative? And this could be difficult for some students. Maybe use yellow. So I have this derivative. It's the derivative of the function, or this function, taking into account that this is my variable x. How do you proceed? What is the derivative in this case?
1 over I.
Thank you so much. X over I, the derivative is gonna be 1 over I. And what happens if I put the x instead of I, like in this case? In other words, I can write u over x. What will be the derivative?
Minus U over I squared.
Minus u over I squared. I remember Carl being really good in those. Carl, we really need your help to, as a team, give us ideas and so on and so forth. So I is known in this manual, it's here, it's 20.02 milliamperes to be converted to amperes. And U as well is 3.2 volts. You plug in all the values and you simplify your answer to 1 sig fig, add a unit to it. Anybody has an answer for the error on R? And maybe I can crop this guy. Let me crop this guy and insert in our document. Yes, I need an answer.
I got 0.5 times 10.
0.5 times 10. You wrote it because you wanted to hit some significant figure. Why didn't you write 5? Isn't it the same?
Because we do not have the same number of decimals like R.
All right.
And I wrote R 1.59 times 10 to the power 2.
Okay. Although you don't really have to do this, you can simply say 1.59 can be rounded to 1.60, but it has to be 3 significant figures like this, plus or minus, 1 second, plus or minus 5 ohms. Okay, we can do this. Or 0.5. Okay, let me follow your work. You want to do this times 10 plus or minus 0.5 times 10. Okay, was it Carl talking? And maybe add ohms in here. Okay, this sounds a little bit confusing. I can simply say this is 160, but the problem with 160, it's 2 sig fig, and I want to keep the 0. And I can write 160 points, you know? or keep it as such. As long as they look similar, it's important to have one sig fig in here or in here, and then make sure these two are similar in rounding, okay? I'm gonna keep on giving you examples throughout the semester. Let me save this one, and I promise to add, how do I add a choose? Okay, I need to add what we already wrote for you to keep. Maybe it will be a good idea. Give me a moment. Maybe share it with you. Okay, this looks huge. Maybe I can share it somewhere here. Okay. All right. Let me save it and see how I can share it with you later on. Maybe update our old file. All right. That's it for data analysis. I know that your class need a lot of practice, so maybe include a practice every week. Now it's time to move to lab 1. Okay. Lab 1. This is it, description of motion. This is one of the most interesting labs you guys will see in Physics 111, which means if we ever go back to our campus, I really need us to do the experiments again, okay? I recorded myself doing the experiment, so maybe show you the recording first, then the theoretical background, because the recording is awesome to listen to. I divided the recording into 3 movies, as you see, motion 1, 2, and 3, all of which are uploaded on YouTube for LAU, so I can give you the link, okay? Maybe I went really slow, but I really wanted you to live the experiment, and I did some mistakes for you to see what mistakes you should do, okay? I'm gonna click play and pause every now and then to explain. Stop me if you have a question. Hello everyone. This experiment is the first experiment you will have to cover in mechanics lab. It's labeled description of motion. Let me start with, so here you don't really see the screen, but there are another caption in which you will actually see what's inside. But for this section of the video, I wanted you to see the motion sensor and explain the functioning of it. Listen well, because you may be asked about the functioning of the motion sensor. Is the equipment needed? You will need a motion sensor. This is a motion sensor. And your computer, all right? Let me tell you exactly where I go. So basically, you are supposed to go into the mechanics folder. You double click on mechanics folder. You have to cover position and time and velocity and time. So this is called Data Studio. You will learn how to use it in a moment. I will be minimizing this window and maximizing this window. So your job is... Okay, so here it's not really visible, but in a moment, I will show. Okay, now listen about the motion sensor. Now, how does the motion sensor work? It's a very user-friendly sensor. It does not need any calibration or any zeroing or anything of the sort. You just have to click start on Data Studio, and this one starts making measurements. How does it go? It sends ultrasounds. They go at a certain speed. You know, ultrasounds are mechanical waves. They have a certain speed. It's a longitudinal wave. You cannot hear them. They're outside the range of your hearing abilities as a human. So the ultrasounds will go. They hit a certain obstacle and they come back to the motion sensor. The motion sensor is an emitter and a receiver at the same time. So it can calculate the time taken by the wave to go and come back. Knowing the speed of the wave, it can tell the distance covered. You know, speed equals distance over time. So it can, using the software, you can tell the distance covered, and therefore you can tell the position of the motion sensor with respect to the obstacle, or the position of the obstacle with respect to the motion sensor. So this tool will help you along with Data Studio to create position time graphs, velocity time graphs, and acceleration time graphs. All right, do you know any tool that you can use in your daily life that is very similar to the motion sensor? This one. That sends ultrasounds, they hit an obstacle, and they can tell you the position of the obstacle.
Sorry, doctor.
Yes?
Isn't this infrared or it's ultrasound?
This one is ultrasound, but other tools would give you the same measurement, and they are usually infrared. The difference between infrared and ultrasound, infrared can propagate everywhere in vacuum as well. But
Yes, I know.
ultrasounds, yeah, so this is a little bit limited, if I may say, but this is how our motion sensor functions. Okay? I want you to see this video. It shows you exactly how to use Data Studio. Right? Check it out. You will have to find a folder called Mechanics. This is Mechanics. You will have to cover position time graph and velocity time graph. So let me go into position time graph. How does this activity functions? First of all, you minimize the workbook, you maximize your graph. Are you being able to see that this is position versus time? Position is in meters and time is in seconds, all right? And this is a graph that we are supposed to match. So it's a template. I'm gonna move the motion sensor away from a certain obstacle and I'm gonna try to mimic exactly the same template. How do I do so? I start by clicking start and stop. I suppose you can see this knob and see how it works. How about we try this together? I got us here a red notebook, and this is my motion sensor. I'm gonna put my motion sensor to be at a certain fixed position, and I'm gonna move the obstacle. I will try to do the same template. If you can see my screen, I will click on start. I can hear some tick-tick sound. It means that my motion sensor is functioning. So you see some random graph. Yeah, this is only to make sure the motion sensor is functioning. I will click on the first one, run, experiment, delete last data. And now I will try to mimic exactly the same behavior, the same template. You see my position? It's not on 0.4 meters. You can see here the notebook is not moving at all. That's why you have a constant horizontal line. All right, so the problem with these graphs, you won't be able to know how to do the motion if you don't understand what they are. So how about I take a small break and I go back to my PowerPoint presentation discussing what are position time graphs, okay? Shall we do that? Yes?
Yes.
All right.
Yes.
Yes.
Okay, so my question for you is, how do you describe motion? Let's say you have anything, a pet, a ball, a tennis ball, I don't know, a child on a skateboard. How do you describe the motion? What do you use as terms? Let's write it down. So what do you use?
And time.
Time?
And distance.
Okay, distance. What else?
Velocity.
Acceleration.
Velocity. Acceleration. Okay. All right. So this is only to describe the motion without understanding why the child is moving. Do you care about the why? Maybe the child is moving because he wants to go and pick that chocolate, or because the child is happy or angry. I don't care about the why. I just want to describe, and describe means this is kinematics. Kinematics means I'm only describing what's happening, and description is important because it can tell me what will happen in few minutes as well. So there is a lot of, let me say, prediction in this one, okay? This is the motion sensor we've been describing. You see how it looks like. This LED will tell you if it's functioning or not. There's a button in here, a switch, that you can narrow the signal and make it wider. Initially it was wide, it was hitting the wall, and I had to narrow it to hit only the notebook. There's an angle adjustment. I can turn the motion sensor a little bit downward or upward, facing the ceiling maybe. And I can connect it to my eventually to a track, to a rod, clamp, anything I want. So this is how it looks like. Now I need to discuss the different types of motion. I can think of the URM, that stands for Uniform Rectilinear Motion, and UARM, which stands for uniformly accelerated rectilinear motion. I don't know if you ever heard of these. Maybe together write some definitions. So what do you expect uniformly rectilinear motion to look like? Can you define it? Can you help me define it? Yes.
It's constant acceleration.
Okay, I would say that the acceleration small a is actually zero. What's
Zero,
constant
the velocity
the
is
V.
constant.
Okay, so this
Zero.
guy is actually constant. All right, how about this one? It's uniformly accelerated. So what do you say?
The A is constant, the acceleration is constant.
Okay, so A is the one that is constant. And how do you compute V?
It's about time. It has time.
It is
Velocity.
time related. So I'm gonna say it's my V initial and add to it A times time. Okay, we all know that the definition for acceleration is actually a V minus V initial, so the change in velocity over time. So if you really look into it, V final will be A times T plus V initial, or this one. Okay, can you tell me a little bit about the distance covered, X, in the case of URM? Can I say it is a function of time?
Yes.
My position is varying
No,
with
it's
time.
X is constant.
X constant means X is equal to 4 meters. It means I'm not moving at all. So this means at rest. Although I'm
sorry.
talking about a certain motion. So what you just said is wrong. So X cannot be constant because constant means not moving and constant means at rest. I need my X to be varying in a linear way. Like I would be either moving forward at a constant speed or moving backward at a constant speed. So a good thing will be, it will be my initial position.
I plus VT.
Yeah, plus VT, stating that my position right now is my old position plus VT. Remember, VT is a distance covered. So all that is the distance covered. So it's my old position, you add to it the distance covered. Okay, this one is a little bit difficult to guess. It's gonna be your old position plus a certain V times time. It's gonna be V initial times time plus a certain half. Okay, that's gonna be a plus half times A times T squared. Okay, maybe you know this one, maybe not. By the way, those multiplication are confusing. Let me put a dot because they're really ugly and they look like X. Okay, so keep it as a dot. All right, so maybe you know this from the course, maybe not yet, and I don't really care about it at the moment. I just want you to understand the basics. So anything that I will be discussing now will be very descriptive. This one, I need somebody, okay, this is a position time graph. I need somebody to help me describe the motion. So how do you describe the motion? What is the guy doing in this case? Motion, what's constant?
Velocity is constant.
Okay, can you, okay, are you moving forward or backward?
Forward.
Okay, I can see my position was 0, then 20, then 40 centimeters, then 60, then 80. All right, so this is moving forward at a constant speed. Do you agree? Okay. Shall we move to a new example? Do you all agree? Okay, let me check this one and insert another text box. Okay. Who can explain this one? It's made of 3 different motions. Maybe divide them into 3 different motion explicitly. I need somebody, and I want the girls to speak up as well. Leia, Rima, and I don't know if Dana joined us. How do you describe the first part? So what I mean by one, this is the first part of the motion, this is the second part, and this is the third part. How do you describe it? Yes, I'm all ears.
So number 1 is accelerating.
I would say moving forward. Shall we say that?
Yeah.
Okay, accelerating or not, we'll check this later. What about 2?
And number 2 is at rest.
Not moving, at rest. Okay.
Number 3, can we say decelerating?
No, it's not decelerating because you are at position 3. You go back to 2.5, then 2, then 1.5, then 1. This is moving backwards if you think about it. Okay? And maybe I need to remind you, or maybe you don't know this yet, that the slope in this graph, slope in a position time graph, what is it? The slope, what does it represent? Slope in a position time graph.
The slope is delta x, that's y or delta x.
It is the change in position over change in time, which is velocity. Excellent. And you can see, I don't know if Leah was the one talking, I was not following on your name. Do you see that the slope is constant? Yes?
Correct. Correct, yeah.
Okay, so since the slope is constant, it means that the velocity is constant, Leah, which means moving forward at a constant speed. Okay? And you see the slope is positive. So slope positive means forward because velocity positive. And this one, you see that the slope is equal to 0, meaning velocity equals to 0. Okay? And this one,
I have a question.
yes.
For number 3, if number 1 is moving at a
So this is constant speed. This is constant speed, positive. This is 0 speed, and this is negative speed. Maybe I can write it down in red. So the speed here is constant and positive. The speed here is equal to 0. This is very important, by the way, like extremely important. And this is constant and negative. Positive means forward or positive direction. This is backward or negative direction, and this is no motion at all. Okay, did I answer your question, Leah?
But I'm being...
It was Rima.
Okay, Rima was asking the question. Okay. Did I answer your question anyway?
Thank you.
Okay. So that was a little bit more difficult than this one. Can we try this one? I'm still doing position time graph, and I want to label 1, 2, and 3, and 4. Maybe not split 3 and 4, but split it anyway, why not? And insert a text box to be able to explain. Who can help me for item 1?
It's moving forward and the velocity is positive.
V positive, V constant. Okay, so moving forward at a constant speed. Okay, 1 second. Oops, what just happened? Undo. Okay, I'm glad undo works. Do we all agree for item 1? Yes? Okay, now item 2. How do you describe item 2?
Velocity 0, not moving.
Okay, at rest, I would say V is equal to 0. Item 3, what do you say?
Or moving backward, but beyond the rest point, or beyond the start point.
Okay, V constant. I like this. Who was talking? Was it you, Nazir? No, not Nazir. I don't know anybody. Who said beyond the starting point?
I did.
Joseph, right? Yes, Joseph. So, yes, you move backwards until the starting point and you continue beyond the starting point. So, this is not really, this point is not the resting point or it's only the starting point. It has nothing special about it, that the position is 0, all right? So, it could be anywhere on the track. So, that's why I divided 3 and 4. So, 3 and 4 are exactly the same thing, which means in motion number 4, I'm still moving backwards with the same constant speed. What about item 5? What do you do? Yes.
Item 5, it's moving forward. The velocity is moving velocity is negative.
Okay, V
It is
is
negative direction.
actually
Negative direction.
positive and V is constant. So,
Oh,
so which means you can just, okay, maybe I can draw a ruler. I'm actually standing on a ruler. Let me draw it straight. So this is a ruler. I have 0 in here. I have 80 in here. Okay, 80 meters. And I have negative 50, no, negative 40. So what happens is the following. And this is our guy. Let me call him Joseph. So Joseph was actually on 0. He would move forward until position 60, will be at rest for a while at position 60, then would move backward to position 0, and then keep on moving backward until he hits negative 40, then move forwards to 0. So this case, Nazir, is nothing but moving forward while stepping on the calculator on the negative graduations. But who cares about negative graduations? Like, I'm behind the starting point, but I'm still moving forward with a positive velocity, okay?
all right. Thank you.
Okay, let's try this one, position time. Okay, this is the last one in our position time. And let's try, I know this is overwhelming. It's already labeled A, B, C, D between A and B. I know it's overwhelming, but I truly believe this is a very important application for us. Okay, maybe move this to the side. Okay, help me out. Between A and B, what happens? Between A to B. Again, position time. This is A to B. What's happening?
It's not moving.
Excellent, Leah. So this is at rest at position X is equal to negative 5 meters. I'm not moving at all. All right, now let's try from B to C what happens. Am I moving forward or backwards?
Yes, moving forward.
I love
V
this.
is
Yes.
constant.
Okay, V equals positive equals constant. I like this. Okay, then what happens?
Is it positive?
Yeah, positive because positive slope. Okay.
Okay.
Even if my position is on the negative side, I don't care. Okay. Now between C and D, what's happening?
At rest.
At rest, at position, if you want, X equals negative 2 meters. And then between D and E, I can take it as one chunk, I don't care. Forward or backward motion? Between forward, because the slope is positive. I'm gonna say V equals positive equals constant. My question is for you before we move on. Let me just state this to be 1 and 2. Can you tell me where the speed is faster, on 1 or 2? Does it show? In other words, in which case the slope is higher, 1 or 2? Yeah, 2 is a little bit steeper. Yeah, but I'm not sure though. It's a little bit steeper. The best way is to do rise over run. This is the rise, this is the run, and calculate like the run. Maybe you do it later. I don't really care at the moment, but it shows like 2 is a little bit faster. Let's continue. E and F. Anybody other than Leah? I would happy to listen to Joseph and Rima. So E and F. Who else? Do we have other? Yes.
Is at rest?
Yes, it is at rest. So not moving, or let me say at rest, at position what? 8 meters, right? Yeah. Okay, finally F to G.
Moving backwards.
Yes, moving backwards. So V is gonna be negative and constant. Okay, I always type wrong. What's happening? Okay, I'm not patient. All right, so we took a lot of time to discuss position time graph and you did well. Now we need to move to velocity time graphs, and here we have many parameters to consider. They may be a little bit more difficult, okay? This is a velocity time graph. You need to understand that it shows you velocity and acceleration. And before inserting any description, I would like to write some general terms. If I'm gonna start with if V is positive and A is positive, can you tell me how would you describe this motion? V positive, A positive. Are you speeding up or slowing down?
Accelerating.
Okay, which means speeding up, I suppose, right?
Yeah.
Are you moving forward or backwards?
Forward.
Okay.
Forward.
How do you know it's forward? Who decides about forward? Is it V?
Because the V is positive.
Okay.
Yeah.
So to know forward or backwards, we need really to consider V. Okay. Please mute your. Yes, mute yourself because I can hear my voice, Joseph. All right. Now V is positive and A is negative. What happens?
You are moving forward, but decelerating.
Okay, so this is slowing down because the acceleration that is proportional to the pulling force is opposite to my motion, so it's gonna slow me down. Why is it backward? Because I look for the velocity every time. No, it is forward because the velocity is positive. Every time I want to discuss forward or backward, I look for the velocity. Now, what if V is negative and A is negative? What do you say will happen?
Speeding up, speeding up.
Speeding up because they are both pointing in the same direction. Is it backward or forward? It is backward because V is negative. And the last one is V negative and A positive. What do you think would happen in this case?
Slowing down.
This is slowing down because they're pointing in opposite direction. Forward or
Backward,
backward?
backward.
Backward. Awesome. Okay, so to be able to discuss the motion in here, I'm gonna pick a pen, let's say blue, to discuss the V's, and then another pen, maybe green, to discuss the A's. So maybe ask Joseph. Joseph, in your case, and maybe have a look at your names. Let me check your names, because probably I have other students as well that would want to talk with us. So I can check on everyone else. All right, Dana signed up or not yet? Michelle, Fadi. Okay, so back to Carl maybe. Carl, I want you to discuss the V in this case. Can I say V is positive, negative, or zero? Carl?
Positive.
Positive. In this case?
Yes.
Positive, negative?
Also positive.
Positive. And this case?
Also positive.
Okay, so V is not the slope. V is the actual y-axis. And all the cases are above the zero. So it's very easy to tell. Now, Carl, can you tell me about the acceleration in this case? It's the slope.
It's positive.
Positive slope. What about this one here?
Zero.
Zero slope. And what about this one?
Negative.
Negative slope. Awesome. So now I can simply follow this. Like here, you're speeding up forward, constant speed forward, and slowing down forward, as you can tell. So every time you have a velocity time graph, please take your time to write the V's and the A's, then come up with a description, okay? Otherwise, it's gonna be confusing. So all this is a forward motion, speeding up, then constant, then slowing back down to rest, okay? So let us try this one. Maybe write the V's and the A's. Maybe ask Leah. Leah, help me with the V's. First part of the motion, V positive, negative, or zero?
Positive.
This one is V
V
positive.
positive.
And next?
Zero.
No, that's positive because the V is the next
So
one.
yes, okay.
And this one?
Positive also, but after
Yes.
10, it's negative.
Awesome. Which means when you see a line as such, you're switching from forward motion to backward motion. And this is at rest. This is the position that tells you that you are at rest, okay? Like in a position time graph, this line doesn't really matter. We took it as one chunk. But in a velocity time graph, it's a drastic change in motion. Now for the acceleration, Leah as well. Can you please tell me about the slope?
Okay, it's positive,
Yes, then,
then 0,
yes.
then it's negative.
I love this. Awesome. Then,
Also negative.
okay, so you can see speeding up, constant speed, slowing down, and then speeding up again. And you can see forward, 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 then backwards. I'm still following this scheme that is here. Let me zoom out. So this is a very important thing to keep in mind. This is only for velocity time graph. We did this one. Is that the last slide? We still have slide number 12. This is easy. Maybe ask Joseph to do this one. Please, Joseph, tell me about V, then about A.
V is positive, A is constant.
Is A constant?
Positive.
Yes, it is constant, and yes, it is positive. So how do you describe the motion in this case?
True, uniform.
Okay, I'm gonna say forward.
A is uniform.
Forward. I'm gonna say speeding up. I'm gonna say A is equal to constant. You wanna say it is a UARM motion, you can say that. So it's a uniformly accelerated rectilinear motion. Do I know if it's rectilinear? I don't know. Maybe. The only way to tell if it's rectilinear or not is to know if it's on a straight line or not. What if it's taking some turns right and left? I know that velocity shows the vector, and I don't see any change in direction, so I'm gonna assume it's rectilinear, okay? Joseph, can you help me out with this one? It doesn't sound very difficult. Let's start with the V's, then with the A's. Can I say that V is positive everywhere? Because it's above the zero axis?
Yes.
Okay, now help me with the slope, acceleration. This case, slope
accelerating.
Is, so this is positive.
Constant 0.
This is
accelerating, decelerating. في constant, I guess, for rest 0. بس أنجح.
Okay, Joseph, you blew my mind away. You just said constant, rest, 0, أنجح. You gave me like 1 million description. You have to be very specific. And let's try to be mathematical, then descriptive. So far the slope is positive, slope 0, slope positive, and here I have...
it is 0, I guess.
This is slope negative, right? And here I have a sudden change in slope. But it means nothing. This is forward, and this is forward. This is speeding up, and this is slowing down. It's as if maybe you hit on the brakes. Maybe. It's the only understanding for me. Maybe you hit an obstacle, I don't know. Or suddenly the road is so thick and friction is very high, because you speed up, then you slow down. So this is not at rest, because at rest means zero velocity. You have to hit this axis to be at rest. Like for example, this is at rest here, because you've hit the zero axis. But here I don't see any at rest. It's a sudden change in the force, like speeding up, suddenly slowing down. So I don't know what it means. Okay, so now I'm gonna save this and move back to the videos, because in the first video you saw, I was showing you how to proceed. Did I finish? Okay, we did all of this. Okay, yes. And then let me keep it, maybe we need it. Now video number 2, I was showing you how to do the motion, and I stopped halfway through here. Let me delete this. So you see, it gave me a horizontal line, that's a position time, because the notebook was not moving. So this means at rest. This is a very nice experiment. I really want you to try it. It's so much fun. I can hear students like screaming out of laughter because of this one. And try another one. Delete last one. Okay. Maybe get a little bit closer. This is the first line. If I go forward, you see the line will go downward, so I was supposed to go backwards. So backward was the positive direction. I was standing upside down. So backwards with respect to me is the positive direction. I'm supposed to go away from the motion sensor. It's called experimenting, and I'm doing this part for you since you cannot do it yourself. So let me try again. my position should be 0.4 meters away. Then I will go backwards. You see some discrepancies. So maybe I'm gonna fix that. Okay. I think my motion sensor should be tilted a little bit forward. So I'm rotating it forward. Some very far position, the wall behind me. And let me try again. Now it should work. Position, so position your motion sensor at 0.4 meters away and move backwards at a certain pace. And you see my pace is much slower than what is needed. So I'm supposed to move even a little bit faster. So I'm gonna click on run, experiment. Now it's gonna work. This is what I remember. Again. So position your book, all right? Move backward at a certain pace, all right? Then stop where you have to stop. This is not bad, although I should do something even better than this. Okay, I'm gonna stop the movie because I know you can watch it later, and I'm gonna show you what eventually I got. I got this one. Okay, so this is what I got. So no motion, then moving in the positive direction backwards with respect to me. Let's call it positive direction. I was slow, then fast, then slow. I could not maintain a constant speed. Humans find it very difficult to maintain a constant speed. Then whenever I reached this, I tried not to move at all. And this is what I recorded. Okay, I'm gonna send you this as a result of my experiment, which is me trying to match the template graph. Okay, now I want us to move, if I'm not mistaken, to the third motion video where I have to mimic a velocity time graph. Velocity versus time. Now you will be surprised with a graph that is actually really complex. So this is a very complex graph. You need to move in the negative direction, speed up, slow down, and then move in the positive direction, speed up, slow down. Speed up, slow down, speed up, slow down. And you see this very tiny straight line that says constant speed? Nobody can do it because nobody can move at a constant speed over half a second. It's so fast. And anyway, you guys, you cannot control a constant speed with your hands. So if I can do a peak at the same position, it's gonna be good. Look at me, it's gonna be really awful. You need to take your time to study this graph well. I'll take a picture of it so you can have some data. So this is a velocity versus time graph. Velocity in meter per second versus time in seconds. You see velocity 0, then velocity negative, then negative, then negative. Is velocity negative meaning backwards? I don't know, we can try. Velocity 0, which means not moving. Velocity positive, positive. Is this forward, backward, or all of it forward? Does it mean speeding up, slowing down, or is it slowing down, speeding up? We don't know. You have to guess. And I suppose this is really fast because the whole thing is going to happen in 10. By the way, you will be asked in the lab report to describe the motion. So the exercises you're doing today are very beneficial. I will show you the lab report in a moment. Yes. So how about we try? I don't know. What am I doing? I have no idea. This is a really fast one and I need to focus. So start. And then I'm going to just push it backward. And then push it forward. And then push it backward. Okay. This is not bad. I'm going to attempt a better one. All right? Maybe you want to see the camera closer. Or maybe not, because you want to see the notebook as well. How about I delete this one, because there's no change in the scale, and I'm gonna try to do the first one as well. So this one, that was fast. This one was fast as well. I just went. Okay, let me show you another one, this one. Let me try again. This one, and then this one. This one, and then this. Right, this graph is not bad. So you see, it's really difficult to have exactly the same thing. Velocity time graphs are difficult. Position time graphs are easier to get. And this is what I eventually got, and I need to share this with you. Maybe that was my best attempt. As you can see, the beginning was difficult for me because if I move the book just a little bit, it will show a lot of acceleration. But I could do the second, the third, and the fourth. It was not perfect, but it was okay. Maybe in October, if we come back, you can try your own and we can print it out. Maybe you can do much better than this one. I'm definitely sure you can do much better than this. All right, so I'm gonna send you the 3 videos for you to take your time and watch and observe and see the experiment. But now let me show you the lab report, because eventually this is what you need to do over a week. And please don't wait until the end of the deadline, which is Monday, to submit. Submit anytime prior to Monday. Try to do it in a day or two, okay? I think these, yes? Okay, so kinematics, I'm gonna change the title for me not to confuse you. Kinematics means description of motion. All right, so it's gonna open. So this is your manual. Let me remove my camera. It tells you the objectives, the material used, the theory, and you have another theory in the PowerPoint presentation. So now you have the full explanation with a summary. Do you remember the V negative, A positive, speeding up backwards? And this is if the slope is constant. This is how the setup looks like. All right. Okay, now the experiment. How close should you be to the motion sensor? You have to go back to the graph I showed you. I mean by graph this one that I'm gonna share with you, this one. You see? So yes, so you're gonna go back to this one, use what's on the y-axis with the unit, what's on the x-axis with the unit, and try to fill in those. So I'm gonna send you this file. You just have to fill it in, save it, and submit it, okay? It has a lot of description. I think anybody can do that in a couple of minutes. Maybe you can do that tomorrow. So yes, you have a week to finish your work, but try not to wait 1 week. Especially when the lab report is as easy as this one, because usually the students do the whole thing in the lab during the 3 hours. Okay, so that's it for today. Next time I see you, I can discuss a little bit your difficulties, the difficulties you had in lab number 1. I can give you 1 example or 2 related to data analysis, because I'm willing to do that every time I see you. Like question and answer, because a good practice would be a good practice for you. And I need to discuss lab number 2. Lab number 2 is gonna be free fall. Free fall is a very easy experiment as well, but maybe in free fall you're gonna need to do some averages and RMS. Okay, which means, but now during motion you don't have data analysis, you only have graph analysis. Any question? Yes? If you believe you have any question during the week, please email me anytime you want, or message me, or anything you want. Just don't keep it for yourself. Yes, you were saying. Yes, somebody had a question? You're good? All right, if you're good, you are dismissed. Have a nice week. Otherwise, stay behind to ask me any question you've got.
Thank you.
Thank you so much.
Enjoy your day. Bye.
Bye-bye.
Very good.